All right. Hello, everyone, and welcome to my FPGA development live stream today. This is a continuation from the previous stream where I've been working on getting the PCI Express DMA engine up and running on the Stratix 10 MX FPGA. All right. So, anyway, before I get too far into things. Quick introduction. So, my name is Alex Ferencic. For those of you who don't know me, I am a postdoctoral researcher at UC San Diego. I work with FPGAs, optical switches, data center networking, a bunch of other fun stuff like that. I'm currently the maintainer of an open source NIC and platform for in-network computing called Corundum. And the work that I'm doing today is kind of related to both the research that I'm doing as well as Corundum itself. So for the research, I need to get Corundum operating on this particular FPGA board, which is a Bitware 520N MX, and this uses a Stratix 10 FPGA, Stratix 10 2100, Stratix 10 MX 2100. Yeah, so the FPGA has 16 gigabytes of HBM, and this board provides PCIe Gen 3x16 and 4 QSFP28 interfaces. And that's about it in terms of I/O. I guess there's a couple of other expansion connectors, but those are the main ones. So what I'm going to be working on today is not on this board, because this board is incredibly loud. I'm going to be using the Stratix 10 MX development kit from Intel, which I have installed in one of my development machines. And what we're going to do is basically pick up where I left off yesterday and attempt to get the design running in hardware. So yesterday I made a huge amount of progress. I was not expecting to accomplish as much as I was able to in terms of getting all of the MMIO and DMA tests to pass, in terms of connecting the new hard IP core model to the generic DMA engine that Corundum uses. So after we got the test benches to pass, I tried running that in the Quartus Prime Pro software, and it failed timing, and it also did not infer any distributed RAM. So we're going to go pick up where we left off and see if we can make some additional progress here. All right, let me get a couple things changed over here. Okay. Let's see here. So the Stratix 10 FPGA has a number of different memory resources that are available. There's ESRAM, there's M20K, and there's MLAB. And the MLABs are the Intel version of distributed RAM. So this means that we're using the actual lookup tables on the FPGA as, small RAMs. So these are generally only used for very shallow memories. So I think the MLABs are capable of storing 32 entries. So each LUT basically becomes a 2-bit by 32 entry RAM. And that's basically the same deal on Xilinx FPGAs. M20K is the block RAM equivalent on Intel devices. These are much larger, but they are not so great if you're building very shallow RAMs, because you end up wasting a lot of storage capability. It turns out that Quartus is very stupid. It does not infer any MLABs ever unless you explicitly tell it to put stuff in an MLAB. Additionally, it's very pedantic about inferring RAMs, and it takes a very close look at exactly how you're using the RAM to make a determination as to whether or not the read-write behavior will match what the hardware is capable of in terms of the M20Ks and the MLABs. And I'm not sure exactly what the issue I was running into, but the bottom line is it wasn't inferring the MLABs as expected. And with some poking around, I found what I think is the solution, and that is to add a bunch of directives here, setting the RAM style to MLAB, and then also adding this no RW check option. So the combination of these two make sure that it actually infers the MLAB, you know, as expected. All right, so what I did is I went through and I found all of the different distributed RAM instances, and I marked those with these attributes. So that seems to have solved the problem in terms of the inference. So what I'm going to do is go and clean up a couple of other things, see if I can get the interrupt subsystem connected up properly, because I previously put this file together, which is the Tcl MSI shim, which is supposed to convert kind of an internal MSI interrupt request connection to the interface on the hard IP core. So I'm going to go ahead and get that set up, and we will see if we can get the whole shebang working in hardware. All right, let's see about that here. So for the Xilinx UltraScale one here, I put the interrupt interface, down here at the bottom. Okay. Yeah, so that'll be the same kind of thing. I'm going to include the interrupt logic in addition to the main data path connections in this adaptation shim. All right, get that lined up. It's going to be for Tcl interrupt interface. Yeah, to do MSIX, it doesn't provide a nice interface for that. You're basically just required to issue the MMIO writes. Well, I guess they're not MMIO in this case, but issue the PCIe write requests, directly. So potentially, if we're going to support MSIX at some point, I'll have to add some additional interface down here to accept that. I also want to get the flow control connection set up, because these are wrong. So let me go take a look at the this test verilog that I had here. Okay, so I had that above the TL config. All right, let me do that. Put that here. Okay, and then I also need to put this in a couple of other places. Let's see. This is going on the example design for the H-tile. Same idea here. This goes above the configuration interface. All right. Okay, there's that. And that also needs to go on FPGA core for the design that we were using here, targeting the Stratix 10 MX board. That goes here. Okay. And I guess I also need to put wires here as well. While I have this in the clipboard, let's make sure to get everything properly wired up. Okay, there's that. Okay, and this is the H-tile. Well, I'll copy that over from here. I interrupt interface. That, and I will go ahead and slap that down. That. Okay. So that's that, and then I need to add this in a couple of other places as well, right? So this one is going to pass that through to the shim. I need that whole thing. Where was I? There we go. All right, so this whole thing, I'm going to go ahead and connect that to the shim here. Configuration, oops, there, I need to go up. All right, let's see here. Okay, there we go. There's the MSI connection. All right. And then finally, I need to go ahead and add the MSI module itself. That's going to go inside of, oh, wait a second, that's the PCIe MSI shim. I need Tcl MSI shim, this one, okay. So this one is then going to go inside of here. So I have the configuration shim, and then down at the bottom, I will add the MSI shim. And I'm going to do the same thing as in the ultrascale shim, where I have a generate block down here that gates whether or not that logic is included. Convert this. All right, so most of these are outputs, except for acknowledge. Go ahead and tie all these off. Okay. These go away. Guy gets tabbed in, replaces the PCIe one. All right, so this goes over here. I count. All right, and then this is the PCIe Tcl MSI instance, and all of these basically just get connected directly. Okay, very cool. Okay, and once more here. Okay. All right, so I'll go ahead and put this in here, and then I'm going to run the test bench again for the example design, and we will see if the test bench passes. See which one of these. That is for the H-tile interface. Actually, I guess I can run this test. Did I have interrupts set up in there? Possibly. Yeah, I did. All right. Let's try that. Run the whole thing along with interrupts, and we'll see if that. Oops. I didn't like something. Okay. PCIe H-tile IF 428 syntax error. Okay, 428. Oh, because I forgot the opening generate. Okay, and that file is not referenced by the make file, so let me go ahead and add that. Let's see, not that one. There we go. Okay, so, oh, I have it commented out. All right. Okay, and now it's unhappy about something here. All right, so let's see, 72 in the shim here. I shim 72. I guess, oh, so hang on a second. So I need to get this mask from the configuration. Yeah, so this one was a port on the Xilinx devices. For the Intel ones, they have to come out of here. So config MSI. Well, here's the MSI address and the MSI mask. Do I need the address? I don't think I need the address, but I do need the mask. All right, so I need to make that connection in the tile as well here. Let's see here. I guess I need to add another section to this, basically. All right, so this is the where was it? MSI mask. Yeah. All right, MSI mask, and then this is going to be set to not a reg, but there we go. Okay. So I have an MSI mask here. Okay, and then that's going to be passed into the MSI code. So this is necessary to make sure you're not trying to generate interrupts for MSI numbers that are not enabled. All right, so this is going to be configuration. Okay. So I'm going to go ahead and copy that, and we'll go back to the MSI shim, and I will add that to the bottom. So I do that. All right, so this is now input wire. The MSI mask is 32 bits. Okay, cool. So that then replaces This is just the message enable mask. Right. Okay, cool. Wait, is that what I want? I guess there's two components to this. Let me take a look at the MSI capability structure real quick so I get this right. Okay, PCIe Gen 4 specification. I want MSI capability, which should be down here somewhere. Unless I need to go look at the even older one. Oh, here we go. MSI capability structure. Okay, so that's going to be the mask bits. The one that I need is something else, I think. In message control, there is a field in message control that indicates how many messages are enabled, right? Multiple message enable. Yes, that's what I want. Okay. I actually need both of these. Let me take a look. I think there's also something about that in here. MSI, multiple MSI enable. There we go. That's what I need. All right, we copy that, and we will make that connection as well. Okay, that goes up here. Other wire. Yep. Okay. Move that up. Okay. All right. So each of these two signals has an important purpose. This one says these are all of the MSI channels that are, enabled for use, period. And then this one is indicating which ones are, masked by software, saying we don't want to generate any of these right now. All right, so this one is 3 bits. Okay, so that one replaces this one. Okay, cool. And then the MSI mask, this one is going to replace let me see here. Okay, so that one replaces this guy here. Okay. Why is this repeating this low bit? Config interrupt MSI enable 0. Let me take a look at what the heck this signal is doing on the ultrascale device, just so I get this right. It's also possible that the ultrascale one is wrong. Let's see, where did I put that? Is it this one? Okay. Interrupt interface here, MSI interrupt interface. Okay, so that's the interrupt input. MSI sent, MSI fail, MM enable. All right, so why? Oh, that's a different connection there. That's just MSI enable. Okay. So I think I need that bit as well, actually. I need yet another connection. Okay, so if I go to config, there should also be an MSI enable. There we go, config MSI enable. All right. Okay, so I'm going to go ahead and make that connection as well. Okay, that's just whether any MSI is enabled. Okay, so I have that. That one is going to be connected. I think I might need to put the other one. Where did this go? Multiple MSI enable. Multiple MSI enable. I forgot to connect that. Okay, mask enable. Oh, this should be CFG MSI mask, right? Okay. Okay, that seems more reasonable. Okay, cool. All right, where was I? So I need to add now this config MSI enable. That's just a 1-bit signal. All right, cool. Okay, that one then replaces this. Okay, and then the message enable mask coming from here. CFG MSI mask. Yeah, okay. All right, I think. All right, so CFG interrupt MSI enable. That replaces this one. Gotta finish removing all of the old ultra scale stuff. All right, MSI IRQ active. All right, that seems all fine. All right. Maybe I finally have this sorted out. Let's try running that test bench again. Syntax error, line 60. Tcl MSI. I forgot a comma. Actually, neither of these are saved, right? Let me make sure those files are saved here. Okay. Alright, and then we also have another wire, line 79. Unable to bind. Yeah, each tile MSI.v line 79. Oh. There's something way over here. I see. That should be the multiple message enables. Yes, okay. Okay. Try that again. Okay. Now this is running the DMA tests. This shouldn't affect that, so what I'm going to actually do is go in and disable these tests here, and I'm just going to run the MSI test. Okay, just with the MSI test, nothing else. And it didn't work. Alright, well that's fine. Let's see what happened. First I'll refresh this. Okay. I gotta go into the generate block for the MSI module here, and we'll take a look at that. MSI ACK is Z. So something didn't get hooked up. Oh, I think what I need to do, I think I forgot to make the connections over here. Yes, I did. Alright, well, no wonder it didn't work. Let's try that again. Alright, still didn't work. This up then, I hit refresh. Okay, so something happened. Let's see here. So, let's see. Where is the app MSI request? Right, that goes high. And MSI num is 1. I don't think that's quite right. I think that should be, I think it should be trying MSI 0. Oh, I think I might know what the issue is here. Hang on a second. Okay, so when it sets, let's see here, the output that's being generated here in terms of the MSI num, oh, MSI int reg. All right, MSI int next, that was sent to, I want to set that to grant encoded. Okay. Let's try that. That should actually provide the MSI number this time. Oops. I don't have that signal declared. All right. All right. So that will be 5 bits wide there. Okay. Cool. I need to use a priority encoder here to select, who gets to send it MSI. Okay. Hey, there we go. That passed. It fired off all the MSIs. We can go take a look at this. There we go. That was 0. That's 1. So on and so forth. That looks good. Actually, I guess I need to hold this. So MSI int next. This is going to be MSI int reg. So I will hold that so that doesn't get changed. Okay. Cool. There we go. That looks better. All right. Great. So now I'm going to go ahead and enable all those tests again. And then we'll also run the example design test bench, and then we will run or attempt to run this on the hardware. Okay, so the full test, we'll run that. And the example design test bench, I think I had around here somewhere. Oh, that's the project. That's the H-tile. All right, I don't have the example design test bench open at the moment, do I? This should be the right one. Oh, I need to turn on the MSI. Okay, and if I go to, let's see, FPGA core here, I have those on one end, but not on the other end. All right, let me make that connection real quick. I think I put those in here. Yep, the H-tile interrupt interface. Oh, and I also want to just make the connections for the flow control signals as well, because what I want to do later is put a logic analyzer on those so we can try to get a sense of what the heck the flow control connections are doing. Because as of right now, I don't know what the story is with the flow control connections. So I'm going to copy these out of here. I need to change all the directions, but okay, that's fine. Oh, let me actually make sure that all the directions are correct here. If I've been copying and pasting that thing, but haven't taken a close look at whether the directions are right. Yeah, that looks fine. Okay. So the interrupt interface, and then the flow control, these are all the flow control signals. All right, cool. And they're all going to be inputs from this end here. Okay, input. All right, there we go. That's all the flow control connections. So I'm going to go ahead and transfer these over to all of the other files that are relevant here. All right, so I need them here. Flow control signals. Let's see, I had these right between the interrupt interface. Okay. Okay, there's that. And let's see, where else does this need to go? Put this here. I think I put them here yet. So right, that will replace that. So that'll be another component to include in this shim is any kind of processing that needs to take place for these flow control signals to get it into a form that the DMA engine will be able to use it. All right, so we got those. And what else do I need to do with those guys? So FPGA core, I added them. Oh, I have not added them here yet. Okay. So here, that, okay. And then all of these signals need to be passed through the model, or to the core logic of the example design here. Okay. Okay, that looks good. Go ahead and take this and copy this. Actually, one thing that I need to do, this one is not pointing at FPGA core right now, so I'm going to go ahead and change that. Okay. That one points here, and that one, that should be connected. Okay, and then down here for the H-tile, I need to pass this connection through into shim here. Okay. All right. Opened up the test bench, so I'm going to go ahead and run the test bench now here. I probably need to add a file to this. Or maybe not. I guess I already did that. Okay, let's see if the interrupt fired. Oh, I may also need to connect. So there's an MSI IRQ here. I don't see the interrupt firing. Let me make sure I got everything wired up correctly. All right, let's take a look at the waveforms. all the way down and take a look at MSI module here and make sure I need to connect that at the test bench level, don't I? Alright, where was that? Here's the FPGA core test for this guy. Alright, and I need to go in and add the interrupt interface here and also the flow control interface, right? Because we want to see if those are doing what they're supposed to do. Okay, run that again. Hit refresh here. Still didn't work. Okay, so MSI goes high. Where's the MSI IRQ input? Oh, so that's never even issued. I see. I think I added an interrupt enable at some point, and I think the test bench code that I have doesn't actually set that bit, does it? That's possible. Alright, well, let me see about this here. So in the core logic here, that bit is going to be, where is that? Read and write interrupts. That's offset 8 here. Okay, so I'm going to go ahead and set that in the test bench, and we'll see if that works. Where was that file? Here it is. Okay, so let's see. Enable DMA, and I need to enable interrupts. So that's offset 8. I want to write bit 3, or I want to write hex 3. Okay. Let's try this again and see if it actually triggers an interrupt. MSI interrupt 0. Okay, there we go. Fired it there, and I should see it again here. MSI interrupt 0. Okay, very cool. So that should be firing twice. Bang, bang. Perfect. Okay, that looks good. So at this point, if all the connections have been made at the top level, I think I've got one end of all of these. I need to go put the other end in. Okay, let's see. Where is the MSI connection here? App MSI request. Okay, app MSI acknowledge. App MSI TC. App MSI num. And app MSI function number. Okay, and then I'm also going to wire up all these, all the TX credits. Okay, that looks good. So at this point, I think I'm ready to try firing this off in Quartus, and we'll see what happens. Yeah, okay. Alright, I think, when I was screwing around with this last night, yeah, okay. I don't think I have a logic analyzer attached right now, so we're going to go ahead and build this and see what it looks like. And if it closes timing and looks okay, then we'll add the logic analyzer and we can take a look at what those flow control connections are doing. This will take a few minutes to build. Alright, so let's see. What else is there to get squared away with this thing? So I think the main thing now is, the main thing left is getting the, well, 2 different flavors of flow control operational. Oops. Quartus is not happy about something. Oh, I think I might have forgotten to add that file. Okay, a couple of things have not been declared. CPLD credits and non-posted data credits. What? Okay, hang on a second. This is an FPGA.v here. I thought I got all the signals that were laid out in the manual here. Where was that one? Yeah, okay. So let's see here. The TX credit interface. Posted header, posted data, non-posted header, non-posted data is LTILE only, apparently. Not available for H-Tile devices. NPD credits. But it is here. Interesting. Okay, whoops. I just won't connect that one then. And CPLD, I think, is the other one. CPLD, yep, okay. I'll also remove that connection. Okay. And then I think I might also need to add the MSI module. Let's see, H-Tile. Yeah, here's the configuration one, but I need to add the MSI one. All right. Saved here real quick. Go ahead and add that file. Add file. And this is going to be the PCIe RTL PCIe H-Tile MSI.v. Okay. Because it would definitely complain about that. You can't find that file. Okay, let's go ahead and kick that off. It's probably going to give me some other error in 30 seconds. I'll have to go edit something. All right, so what was I talking about before? Right, there's kind of two levels of flow control that need to be sorted out at some point. First one is kind of the ready valid handshaking. And the second one is the credit-based flow control. For some of these cores, like the P-Tile, oh, failed again. All right, can't find port. Oh, FPGA. All right, so I'm just going to remove those a couple of connections. Yeah. Yeah, there's a different setup that needs to be used for reporting errors here, so leave that out. In fact, I may need to remove that from the shim as well. Actually, maybe what I need to do is change the direction on the shim. So those signals can actually pass through to the, I guess that goes to the AER subsystem. And potentially generates messages internally. All right. So, getting back to the PCIe IP cores. On the P-Tile, do I have the documentation for that open, or do I need to go hunt that down? Here's the P-Tile. Okay, so the P-Tile actually has flow control in both directions. So if I go into interfaces, where was this? There's TX flow control and there's also RX flow control. So with this one, you can actually say, don't give me some type of packet and hold it inside of the hard IP core, because there isn't any buffer space available in the FPGA for that type of traffic. But there doesn't seem to be an equivalent interface on the Stratix 10. So basically you have to just exert back pressure against this interface in its entirety and deal with any headline blocking that you might have. There's not much you can do about that. The TX flow control interface seems, I mean, I think it's similar in terms of what information is provided. So this one, it's a time domain multiple access sort of thing. So in this case, instead of having multiple ports, so in this case we have posted header credits, posted data credits, whatnot. This one just has a single credit limit output and then an index, and it cycles through the indices for the 6 types. So you get posted header, non-posted header, completion, or completion header, and then posted data, non-posted data, completion data, and then it cycles through those again. So you don't get instant feedback. It's going to be delayed by a couple of cycles until you get that update. But the question is not so much what's going on here, it's what exactly are these values that are coming out. It seems to be reporting the limit. And as far as I'm aware, these limit values are a little bit annoying to work with because they are kind of a monotonically increasing value. It just increases and then it rolls over. So figuring out how much credit you have requires doing a little bit of additional bookkeeping. Yeah, so that's what's on here. So yeah, what I want to do a little bit later is to put a logic analyzer on these credit connections, so we can see, what's coming out and get an idea of what we're going to have to do to connect these up to the DMA engine. Because I think right now the DMA engine, it's only looking at, it's expecting to see just kind of credits available, which can increase or decrease depending. All right, so it looks like Quartus is doing its thing. We don't have any complaints yet from syntax errors and whatnot, so now potentially we'll get a complaint about something else, but we'll see. All right. Yeah, synthesis was successful. With warnings, apparently. Okay, that's potentially problematic. Let's take a look at that. Partially connected signal tap or other system debug instance. I thought I removed I added a signal tap instance. I thought I pulled it out, but maybe it didn't do that correctly. All right, whatever. We'll be adding a new signal tap instance later on. That should be fine. All right. Oh, is there another one? Quartus Prime is unable to infer placement. Okay. All right, so it seems like those critical warnings are about that signal tap that I added and then removed. I guess I can filter by critical warnings. Yeah, just those two. Okay. All right, so I think we're going to be okay then. All right, so that'll take a few minutes to run. Once that is done, we'll be able to load that on the FPGA and see if it works. Let me actually take a look at the example driver right now and see if that's enabling the interrupt signal or not. If not, then I should probably go ahead and add that. Where was that? That's going to be under common. Common driver sample driver.c. Okay, cool. So I have check DMA enable. Yeah, enable DMA. Okay. Then also I need to make another one of these for enable interrupt. Again, that was going to be writing 3 to offset 8. Okay. All right, so this little kernel driver that I have here doesn't do anything particularly crazy. It does basically exactly the same thing that the test bench does, except it has all of the standard boilerplate you need for setting everything up on the operating system side, enabling interrupts and whatnot. So yeah, this doesn't do all that much. All this is just setting up stuff, and then it does a test access to bar 2, which is that one has the full AXI interface, so you could connect that to DRAM or something if you wanted to. That's mainly a test of the AXI master modules. I mean, not much of a test because it just does a single keyword write and then read, but and then the PCIe DMA test transfers a 512 byte block to the card and then back to the host. So just a very simple test just to get an idea if things are working correctly. So we'll take a look at that as soon as we can get this thing loaded on the FPGA and see if this runs. All right. Well, now we're just waiting on Quartus to do its thing. Once this is done, then we'll go ahead and load that on the card, and, well, if it closes timing, we'll load it on the card and see if it works. Usually takes about 20 minutes or so. So Alex Bedea says there might be some of the project settings to select which signal tap is in use. That's possible. I'm not sure where that would be. And I'm also not sure if I can do much while it's running. But yeah, okay. Guess I can go through and see if there's anything obvious in here. Design units may be listed in here somewhere. Maybe that's where it was getting confused. Not sure. Files, yeah, because I had it, when I created the signal tap instance, it added it to the file list, and then I removed it from the file list, figuring that would be sufficient. But potentially the software is a little bit smarter and it's still looking for it. Yeah, I might need to take a look at that later then. To be honest, it's not particularly important because I can always just create a fresh project later on. So yeah, the whole idea here using the make files and whatnot is that I can just build the complete project from scratch, irrespective of what version of Quartus is installed. Although potentially there are issues with IP. So for Xilinx Ultrascale, or for Vivado, what I've been doing is writing TCL files that generate the IP cores more or less from scratch. And that works out really well because it's basically not tied to the specific IP revision. Because that was always an issue. Previously, I was committing like XCI files for the IP, and every time you upgrade Vivado, all the IP is locked, so none of the make files work. You have to go generate the project file, open it up in Vivado, update the IP, which requires pushing a few buttons, and then you can build it, and then you can overwrite the XCI files with the new ones. Gigantic pain in the butt. Generating from Tcl kind of removes that connection, right? It removes that dependency. And that's definitely helpful with Vivado. Unfortunately, I don't know. I haven't sat down to figure out if there's a way to do kind of the same thing with Quartus Prime, because when I generate the IP, it generates a .ip file that I've been committing to the repository. But that may not be kind of the ideal way of doing things. I know these tools tend to be getting a little bit better in terms of TCL scripting capability, but I have not looked into that in great detail for Quartus Prime. But that's actually kind of important for Corundum, because recently I've been adding these config.tcl things. I guess I might as well just pull this up here so we can take a look at it here. Let's see. So for all the files, or for all of the design variants in Corundum, I have this config.tcl script here, and this allows you to change a whole bunch of parameters. A lot of these end up being passed through to the design as top-level Verilog parameters, but it also goes through and it changes settings on the PCIe hard IP block. So, for example, right now there's an application section inside the design that you can enable or disable, right? So app enable. If it's enabled, the application section gets its own bar. And if it gets a bar, then this will be, reconfigured at the PCIe IP core level to, enable or disable that bar as appropriate. So that's what the setup is here. And it also allows you to set the, vendor ID and device IDs and whatnot without having to go into the IP core settings or edit the TCL script for the IP core itself, for the PCIe IP core. So at some point, I'm going to need to see if there's a way I can do the same thing with Quartus. I think there's a way to set the top-level parameters for all the files, but I don't know if there's an equivalent for editing the IP. So yeah. Anyway, what this file boils down to is two things. It does a bunch of set properties on the PCIe IP, and it also does this set property generic parameter list here. and this ends up setting the parameters that get passed into the top level Verilog file. So all of these basically get exposed to this config.tcl. And the whole point of this whole rigmarole is that you can just copy the make file and the config.tcl script and change any combination of parameters that you want without having to change any of the Verilog, which is, in my mind, a pretty powerful capability. So let's see. For example, if we go into like the ADM PCIe 9v3, do I have two? Yeah. So I have an FPGA and I have FPGA TDMA. And the only difference between these two is the file list in the make file. I think, yeah, right, because the TDMA one pulls in a couple of additional things, and then a couple of settings in the config.tcl. And that's it. And I can actually show, let's see, here's one config.tcl, and there's the other config.tcl. Okay, so I can actually compare these two, right? I can do compare with active tab, and there's, you know, one line different here, right? I've changed the number of transmit queues. And I mean, yeah, you got to duplicate the rest of it, but it's a lot better just duplicating the config.tcl file instead of duplicating a whole bunch of Verilog files, which then have to be kept in sync and whatnot. So yeah, at some point I'm gonna have to figure out if it's possible to do the same thing for the Intel devices. Let's see. And Quartus is still running. Hasn't crashed yet. That's good. Real question is whether it's going to close timing at the end. Right. Oh, yeah. So the other thing that you can do with Tcl-based IP, this has been kind of a continual, you know, evolution. So originally, I was just writing IP or Tcl scripts look like this, and you can more or less extract this from Vivado. If you create the IP in Vivado using the, you know, the GUI. Let's see, I have another Vivado project open right now. If you go down to the TCL console, TCL console, yeah, I think it's a TCL console. It will show what commands were used. So let's see, I think I edited something here. Yeah, so you'll see like a set property command here that's setting a bunch of different parameters. So what you can do is basically copy that out, put it in a TCL script, and it will set up the IP when you source it. So that's what the make file does. It just sets Vivado up to source all of these when you create the project. But you can do more fun stuff than that. This is a file that I have for kind of the latest iteration of the transceiver channels for 10 gig and 25 gig you know, Ethernet PHYs. And what I realized is that I need to create kind of two different instances, one with a PLL and one without a PLL. So I could certainly create two files like this, one for each configuration, or I could get a little bit smart and write a little bit of TCL, which can automatically generate these two with slightly different configurations. Alex Badea is saying that you could also source like some sort of parent.tcl and then set the variables that change. The way it's written right now, I don't think that would work, but potentially it could be kind of massaged a little bit, right? So the problem is at the top of this, I create this params dict, and then I go and set all of the parameters and whatnot, and then at the bottom, I use it. So I guess what you would have to do is kind of encapsulate all of this. So you could change some parameters and then reapply it. The one annoying thing about this set property thing here at the bottom is that this, if you will, clobbers whatever the previous setting was. So this one is just a, you know, a list of all of the top level parameters that are set. I guess potentially what I could do is instead of just creating a, you know, a new dict here, I could try and, you know, extract what was in the current list. Potentially that could be done, and then you could run this multiple times and it would just update, you know, the corresponding parameters. I'm not sure. There's definitely room for improvement here to make this a little bit more streamlined, a little bit more flexible. So, especially some of this kind of boilerplate stuff, maybe it would make sense to put this in, you know, a centralized Tcl script somewhere. Yeah. Anyway, this is the kind of the first more smart technique that I came up with for doing this for Corundum. But obviously, if we need to iterate, then we can iterate, and it's not that big of a deal. You have to do some kind of fun stuff in here for dealing with the PCIe bar sizes and whatnot properly. So yeah, I had to figure some of this out. Like in the bar size setting, it's not like, you know, the width, how many bits. That would be nice. That would be very simple. No, if you want to set a bar size, you do like 16 megabytes or 4 gigabytes or something like that. So I actually have to have a size list where I go look up, you know, the correct entry in here and put it together. Yeah, so it's slightly non-trivial to sort that out. But anyway, it might make sense to take stuff like this and, you know, package it up in, you know, one Tcl script that can be reused. To be honest, I'm not super familiar with Tcl. Even like creating these lists and iterating over that, I had to be like Googling stuff left and right. So perhaps somebody that's a little bit more familiar with Tcl and how Vivado uses Tcl could take a look at this and see if maybe there's a way of reorganizing things to make it a little bit more flexible without obfuscating things too much. Let's see. Right, so I was talking about the IP Tcl things here for this one. Right, yeah, okay, so right, so this one is for setting up the 10 gig transceiver instances for the PHYs. So if you have multiple PHYs in the same transceiver quad, in the same group of 4, one of them needs a PLL and the other 3 don't. So the way this code is set up is that it generates basically 2 copies of the same core, one of them with the PLL in the core and one of them with the PLL outside of the core. So the idea is you can basically cross-connect these using these additional PLL ports, right? We need the PLL lock output, and provides, I think, a couple of the other ports by default. But you cross-connect that, and then it works, basically. So yeah, and this also makes sure that all of the TX and RX settings are configured properly. And I also have a line to compute the QPLL fractional N value, which is rather convenient because it's kind of a pain doing that with the user interface and figuring out what that magic number is for running at particular rates. This is really only necessary if you're trying to run at 25 gig and the board provides reference clock of 156.25 megahertz, because you need a 0.5 in the PLL feedback multiplier, which is slightly annoying. If you're running at 10 gig, 156 is fine, but it seems like it's pretty common for boards to provide a 161 megahertz reference clock, which works at both 10 gig and 25 gig. So, and then the one thing I am working on, well, more like thinking about, is trying to set these up so you can switch between 2 different line rates. So the idea is you can actually configure both PLLs in a quad, one at 10 gig, the other 25 gig, and then you can dynamically switch between whichever one you want to use at any given time. And I think what I've determined for that so far is that the reset network that Xilinx gives you in the GT Wizard is rather terrible, and it doesn't support that. So I'm going to have to turn off the reset networks that it provides and, you know, do that manually. I don't think it's going to be that big of a deal. But yeah, so I got to get the details on that hammered out And then that'll be a nice capability for Corundum, because then you can switch on a per port basis. Do we want to run this at 10 gig or 25 gig? All right, Quartus is doing routing now. Making progress. Definitely taking longer than the run with just a bare core. I think that took about 22 minutes or so, and we're at 23 now, and it's in the middle of routing, so it'll be a few more minutes. All right, let's see. Was there anything else here to be cleaned up? Oh, right, there is no RX flow control. I'm going to go ahead and get rid of that. Those need to be updated as well. The RX flow control, that goes away. Don't have that H-tile model, no RX flow control. I'm just going to continue doing some kind of housekeeping stuff while Quartus is doing its thing. All right, so that goes away. RX flow control. Is there any other RX flow control in here that I need to get rid of? Well, this goes away. That's also for RX flow control. Okay. All right, and a lot of stuff that is going to be more complex to interface if I ever bother implementing that. Okay. Well, if anyone has any questions about anything, go ahead and fire away. I'm just basically killing time until Quartus finishes its thing, and then we can take a look at whether this actually works on the board. Yeah, I guess the one kind of annoying thing about the signal tap in Quartus Prime is you have to build the project first before you can attach probes to stuff. Versus in Vivado, I think you can do mark debug and whatnot before you've built things. And then after you built it the first time, then you actually have that core available. I guess what I can do is take a look at the RX and TX flow control here. So there's a couple of connections here. There's RX ST ready in the receive direction. So this is coming from the IP core. So this is Stratix 10. Let's see, in the receive direction. And let's see, I think there is a diagram showing the ready somewhere. Okay, so RX interface, RX ST valid, deasserts, that's 17 clocks until it actually stops giving you data. Okay, so I think that one is almost ready to go. I just need to adjust the watermark level basically on the FIFOs, because right now I'm looking at half of the FIFO depth. If the FIFO depth is 32, then that's not going to work here. Make that 8, quarter of the FIFO. And I think I had just, yeah, there's another one up here. Okay, cool. During normal operation, these FIFOs should both be basically empty because any TLPs that are ending up in these FIFOs should be getting handled rather quickly by downstream components. Okay, so that's the RX side. The TX side, let's see. What are we doing on the TX side? So the TX side, I think it had a delay of like 3 or 4. Let's see, so the TX ready deasserted has a ready latency of 3 cycles. So that means if ready goes low, that means 3 cycles later you have to put valid low. Oh, and I'm also, let's see, do I have the logic set up for this correctly? Yeah, so this is looking at not output FIFO empty, but I also need to look at, right, so this sets T valid to low because we're not waiting for T ready to go high to accept that. Right, so that's not out full and T valid int. Okay, this is in terms of putting stuff into the FIFO, not out empty and 1. So this one I need to sort out here in terms of flow control. Yeah. So if this has a T ready or a ready latency of 3 cycles, then I think what I can do is just delay the ready by what, 3 cycles, and then use that to gate this. I always feel dirty with this kind of a delay thing. To some extent I understand why it's done. It makes the tools a little bit simpler in terms of what kind of optimizations they can perform and moving registers around, but it's just kind of a pain. Okay, so Twitter is done. Now Quartus is running the timing analysis. All right. Just about ready to run that. I'm going to go ahead and turn on that development machine. Rather convenient that it's a server, because I can just push one button here to turn it on. All right. Okay, so this says the worst case setup slack is 0.114. Assuming that is actually the final number, then that means it closed timing. Sweet. Yep, there we go. It is complaining about something. Partial output delay. Not sure what the story is of that. Maybe I need to remove that line. This is complaining about something inside of the signal tap instance. Okay. Great. That's super helpful. Alright, so I have a bunch of clocks that are not being used. Fine. Improper clock targets. This is another thing inside of the auto-generated stuff. I presume this is associated with the signal tap instance in some way. That's driving clock and enable signals, or both reset and clock enable signals. I'm not really sure why that would be a problem, but okay. Unconstrained says there's some input ports and input port paths. Maybe that's related to like the reference clocks or something like that. I don't think that's an issue. When you're using serializers, the delay of reference clocks and whatnot are pretty much irrelevant. Okay. The assembler was successful. Alright, now it's loading the timing analyzer. Alright, great. So I'm going to go ahead and pull up the JTAG programmer. Well, gotta wait for Quartus to load the timing analysis. I don't know why it opens up the timing analyzer automatically. That's kind of annoying. Alright, so let's try loading this thing. I hit start. There we go. Progress. Okay, successful. Alright, let's take a look now. If I go ahead and SSH into this machine, you won't see anything. I need to reboot it. Do that, re-enumerate the bus. And I also am going to open up a second window here. Well, gotta wait for it to reboot. Alright. Well, I don't need that. Okay. See here, what is the machine doing right now? Like I said, these are server motherboards. They take a minute to reboot. All right, there we go. Got to go through a bunch of different option ROMs. Okay, here we go. All right, well, let's see if it's up now. Okay, should be able to log in. Just networking is being slow coming up, I guess. All right, let me just okay, it did enumerate. Now I need to load the okay, there we go. Now I need to load the device driver. All right. Here we go. That up. So let's see, LSPCI. Make sure everything looks good. Right. So we took a look at this yesterday. Link status 8x8. All right. Perfect. Okay. Let's see here. So we need to go into the driver. All right. I will make that. Okay. Oh. Well, there we go. I see. So this is the test data that was written out into the host DRAM. And this is the test data after the card wrote it back into host DRAM at a different offset. So that's perfect. I see interrupt and I see interrupt. So interrupts are working and the DMA engine is working. Sweet. All right, so now I need to get the, I need to figure out what the story is with flow control so I can enable flow control on there. But yeah, that looks perfect. Okay, I'm going to leave that running for now. Actually, I'm going to RM mod that. Because I need to go add the signal tap now. Okay, there we go. All right, so that is excellent progress. It's not just working in simulation, but it is actually working on the card. All right. So let's see. I think probably the next step is either to try getting Corundum running, or to try to get the DMA benchmark design running. Anyway, what I'm going to do before that is try to get flow control set up correctly. And in order to do that, I need to go ahead and pull up the signal tap logic analyzer and take a look at those flow control signals. All right. Oh, I see. Even though the file isn't in the file list, it apparently still picked it up. Interesting. All right, fair enough. So these are... I guess this is not set up, right? If I hit run here. Oh, I think I had this set up with a trigger condition. That's right. Nope. Okay. All right, let me see here. No records. Oh, because these were all changed up. Right, okay. I wanted to look in FPGA core. All right, there we go. Yeah, that's right. Okay. So I can add the clock. There's the clock connection. All right, now let me go ahead and delete all of these. Okay. Now I can add TX. Search for that. That's looking in the wrong location. All right, cool. Go into core instance again. All right, here we go. Okay, so this will be the TX and all of the TX credit signals. All right, very cool. So I will go ahead and add that. Okay, and then I'm going to do RX, and we'll take a look at the RX signals. All right, there we go. So we got all the TX signals and all the RX signals. Oops. I need to hit the insert button. Ah, okay. That's RX. All right. One more try here. TX, search. Okay. Got all the TX signals. Great. So I will go ahead and add that. And I will hit insert. Okay, there we go. That's better. So I have RxST ready, TXST ready. I have data. Yep, I have the credit signals, data in the other direction. Okay, very cool. Let's make the sample depth a little bigger. Auto segmented, sure. We'll do that. Okay. All right. So for those of you who are not familiar with logic analyzers, there's a bunch of little configuration options. So sample depth is basically the number of samples that you can capture across all these inputs. So I'm saying, okay, we'll do 8,000 samples, which I think is a reasonable size. You can go a little bit bigger. You can also go... I don't know why they give you 0. I just noticed that. That's hilarious. Why? What's the point? I don't know what the deal is with that. Okay. Oh, we have data enable and trigger enable. Okay. I'm actually going to turn off the trigger enable on a couple of things here. I don't need to trigger off a data, and I don't need to trigger off a data here either. And yeah, I'll just leave that as is. Okay, cool. Right. So you can set the sample depth, and then you can also do you can configure segmentation. So with this, we're doing 16 segments. So instead of capturing one shot of 8K, we can capture 16 shots of 512 samples, which is nice because you can set up, you can say, I'm looking for a packet, and then I can capture, 16 packets along with some context on either side. And for the trigger, you can also pick kind of a trigger position. I'm going to pick the central trigger position for the time being, and then I think that'll work. Okay. I think it needs to be saved and whatnot, and then I don't know if this will do a rapid recompile. Maybe it will. Recompile not supported. Well. Go figure. Yeah, so I guess there must be something else connecting this STP file to the project, because I removed it from the file list, but that didn't seem to make an effect. Even though it wasn't in the file list, it still tried to use it. Alright, so we gotta let this rebuild. Hopefully it doesn't take too long, and then I can take a look at what the what some of these signals are doing. Let's see. In the meantime, I guess I can take a look. Well, I can save this, and then that'll use the updated flow control stuff. So let me just restart this here. Yes, stop that and restart it. So that will use the updated RX flow control. So then I just need to figure it out on the TX side. Yeah, I guess flow control is not a particularly high priority if you're not trying to move a huge amount of data. But if you are trying to move a lot of data, then you need to make sure the flow control is set up correctly so all of the data is moved across the link reliably. Actually, I guess what I can do is take a look at the model and see if I can make any tweaks for this to work correctly on... Right, because the way the model's set up right now is it's kind of using the AXI stream type of handshaking. That's not quite right for Avalon. So let's see, we have the sink and we have the source here. So basically these need to be sort of decoupled from the ready connection. So in this case, on the sink, how am I doing this here? Sample valid. Okay, so I don't think I'm looking at the ready signal at all here. So this one is actually fine, I think. Actually, maybe these are correct. Maybe I did tweak these. So this one we're looking at. Oh, I don't think I'm looking at the ready signal at all. I think that's what the story is here. All right, I'm not sure if my test bench is set up to do a proper test of this. I can circle back around to that later. All right, well, we'll let this run, and once this is finished, then I can take a look at those signals on the signal tap and take a look at what's going on with the internal flow control, with the flow control credits. I don't need this anymore. I guess one thing that I could do in the meantime is take a look at the PCIe DMA benchmark design, wherever that one is, and see if I can get the test bench for that running. Okay. All right, so this design here is the PCIe DMA benchmark design. So this one, it's a little bit more, adds a little bit of functionality on top of kind of the default example design that I have for the PCIe, just the PCIe DMA cores. So this one, the idea is you can actually exercise them a little bit more. And eventually this will be used to also test some of the AXI infrastructure and a few other things. All right, so what I'm going to do here is I need to do a couple of things here. So the first thing is I need to go into the common code here and add another one of these for the H tile. DMA bench PCIe US. I'm going to copy that to DMA bench PCIe H tile. All right, and then this one, all right, so this one I'm going to go ahead and take a look at the example design that I have here. Where did I have that? Right, here's the H tile example design. So I'm going to take this and transfer over. Wait, I don't want to do that. Example core PCI. I want to take this, yes, the H tile shim, and transfer that one over. All right. Okay. There's the shim. Now I need to update the core connections here. Oops, I didn't want to replace the clock connections, just these guys. Okay. Okay, that looks better. All right, I gotta update the parameters. All right, and then, okay, these are not -1, are they? Okay, and these same kind of thing, these are all going to be TX sequence num width here. Okay. That looks reasonable, and this is going to be for the Intel H tile. All right. Let's see if I can get the test bench for this running. 100 TB. I need to make a copy of this guy. All right, cool. The H tile. Go ahead and rename this. Okay. And in this case, I need to update all of these to be H tile. IF, I have RX, and I have TX. The other two are the same. Go ahead and just comment out all these parameters for now and update these later. Okay. Now, one thing I do need to do is copy over some of the files that I need here. Okay. Alright, so this is going to be PCIe IF H-tile. Oh, H-tile IF, there we go. But I thought I had the MSI files as well. That's odd. PCIe H-tile. Yeah, okay, there should be 5 files that it transferred over. Oh, because that's not IF, right? Right, MSI and config. Okay, there we go. There we go. That looks better. Alright, so now I have all those files. And I should be able, hopefully, to get that test bench running. Okay, so same kind of thing. Converted a test bench yesterday as well. So let's see. I'm going to go over to, where's the test bench here for this guy? Test FPGA core. All right. So I need to go ahead and transfer over this, which is the PCIe IP core instance here, or the model. Okay, and then I also need to go ahead and swap out that. So I have the root complex, I have the H-tile stuff. Okay. Let's see how badly this blows up. Because I forgot to update this. Okay. Let's run that. Okay. DMA bench PCIe H-tile 130. Oh, I see. It declared that internally, so I don't need to re-declare it. EX sequence number. Ah, yeah, all these go away. Okay. Count with sequence number count. Well, that's just used internally. Okay, so this is, I think, seg count. No. TLP seg count. Okay. Oh, and I think I need to rename this. Yes. Okay. Okay, so this is going to be seg count times seg data width. And it failed. All right. So what happened here? The test DMA, and well, I'll just have to make this with waves. Okay. All right. So let's see here. Let me see, what is the first test that it's trying to run here? So this is the test DMA. Test DMA, receive DLLP, right? Okay, so I get all the way down to the bottom. val equals, all right. Oh, I think there was, hang on a second. Let me take a look at, discovered a bug in here. Okay, nope, I fixed that. All right, so that's not that. Okay, so test DMA, this is going to do a bunch of register writes, and then it's going to actually perform the DMA operations here. Oh, actually, I think I know part of the problem. I need to change a couple of settings down here. The first one is the bus number actually needs to be passed through. That's probably the biggest problem. I need to switch this, and I need to switch that. So those are ultra-scale specific optimizations, those top two. Okay, that went a little bit farther, and then it hit an X. Oops, where are these X's coming from? So that is coming from... Okay, TX read request. Alright, well, let's do a little digging and see if we can figure out where those X's are coming from. Oh, heh. Why is that one called? Alright, so I need to change the name of that module. That's not a, or the instance name. That's not a big deal, but it's like, why is it saying USIF when it isn't? Alright. Let's see. Let me take a look if there's anything funky going on in here. Okay, so the TX credits, all of these are showing Z, which is fine, because those aren't connected to anything. But the more worrying thing is why I'm getting X's here. So this is coming from the TX read request TLP header, and this is going out to the TXST data. So this has got to be coming from the DMA engine itself. The DMA IF PCIe instance. Actually, one thing to take a look at here is I think right now the flow control is not supported at the moment. So, alright, FC enable, those are both set to 0. So it shouldn't be using the flow control, and the sequence number is also set to 0. And the test bench is not overriding those. So what is going on here? Unresolvable bit binary string. Is this just a reset problem? I was looking at this. Okay. So this is hooked up. We got the reset and the clock hooked up. So that should be resetting things properly. Just the clock, right? Alright, let's take a look at the reset line. So this is being reset correctly, right? Alright, so there's a reset doing its thing. Well, I guess I'm just gonna have to check down, or check out what's happening with each of these here, right? So request TLP count reg, request PCIe address. So the only one that's Z is that credit count, but transmit flow control should be turned off, so it shouldn't be looking at that. And in fact, I think that can be checked. There should be a credit available signal somewhere. All right, let me just take a look at the DMA IF code here. All right, read. Let's see. So that signal for credits, that should only be used in a couple of places. Yeah, so have credit reg. We'll be looking at that. And let's see, have credit reg. Have credit reg is X. All right, well, that makes sense, but have credit reg should be ignored if we don't have FC enabled. Right, so this should override that. Yeah, okay. All right, so let's see, dword count, that's all X. All right, so dword count is coming from where? All right, dword count is coming from this whole thing. Okay, so that's fair enough. Last BE is X. Last BE is coming from request PCIe address reg. That one I think was also X. Request PCIe address reg. Request PCIe address, but not the actual reg. Okay, Request TLP count next. I think that's going to be coming from some of these guys. Request TLP count next. Yeah, request TLP count next. That is set by these. So if one of these is an X, let's see. So we've got request op count. Request op count, that's not X. Request PCIe address. Reg, that's fine. Max read request size dword. Let's see, max read request size. Oh, why is that X? Oh, because this is Z. Max read request size. Why would the low order bit be Z? That doesn't make any sense. All right, well, that's definitely why this isn't working. Okay, where is that going to be coming from here? Oh, am I not, Alright, so I have max read request size and max payload size defined here. Alright, so let's take a look at this guy here. Max read request size, max payload size. Where is that signal? Max. Simply not connected somewhere. Oh, because there should be max read request size. And this should be max payload size. Okay. Alright, bus num and X tag enable. Alright. Okay. There we go. I think it's working now. Maybe not. It hung somewhere. Alright, well that's better. Question is now, where did it get stuck? Oh, read statistics counters. Okay, so if it got hung up in the read statistics counters, that must mean that one of these read operations got eaten somewhere. So receive TLP This is xperceive on port.py. Deep TLP. Okay, so got downstream TLP. What this is going to be doing is going through all of the and reading. How would it be doing mem writes? Oh, unless it moved on from the read statistics. That doesn't make any sense. All right. Quartus is in the middle of routing, so it shouldn't be that much longer, I don't think, before we'll be able to take a look at those signals in the signal tab. Okay, so I need to take a look at the test bench again here. And I'm looking at, what was I looking at? Okay, so read statistics counters, that's going to be coming from where? That says 315, right? Okay, so that's this one. Oh, and then I wait 2000. All right, so what am I waiting on at this point? Yeah, so at bottom, okay, so I think what we're seeing here is all of the write operations that were issued right before. So I get all of the memwrite. Right. Okay, so there we go. Memwrite. Maybe that was actually okay. Oh, no, here we go. All right, so we get a memory read here. And then nothing. I see. So it gets all the way down here. It tries to read. It issues a single read operation, and then it doesn't see the response from that. Okay, all right. So that does point in the direction of what's going on here. I don't know if this is a DMA problem or this is probably something wrong in the shim, I think. All right, what time did it send that? So this was sent at 10133. I can go look at that, 10133. Nothing? What? So this should be coming in on the RxST. RxST val. Oh. What happened here? RxST ready goes low. As they say, the plot thickens. What we're seeing here is a transfer takes place from the model into the core, right? And then, or into the shim, and then RxST ready falls because one of the FIFOs fills up. Okay, so then the question is, what is going on in the shim? Let's see, so that's going to be going in. That's going to be on the Rx side, so let's take a look at the Rx code here and see if we can figure out what happened. So this is where the test benches are useful, because I can just very quickly go drill down into the test bench and try to figure out, you know, what happened. Okay. All right, so let's see here. So RxST valid goes high, right? And it starts shifting stuff in. Here we can see it shift a whole bunch of packets in. All right, as it's shifting those in, we should see one of the FIFO pointers updating, right? So I have output request FIFO write pointer reg, so this is incrementing. Okay, and then the read pointer is incrementing, you know, more slowly. So this one stopped at some point, and then these are following with presumably the FIFO being full or almost full. Okay, so I think there's a couple of issues here. Right, so if RxST ready falls, okay, so yeah, this is a problem in the IP core model. Okay, got it. Let's see if I can fix this. Because what's happening is that the FIFOs are expecting, you know, this valid signal to fall, and then they'll actually be able to drain, and then they'll be able to assert ready again. But because that's not happening, actually, what is going on here? So this is RxST data. So this one stops updating, but the valid signal never gets cleared. Okay, that is not what's supposed to be going on here. All right, so that looks like a bug in the interface on the source side. This is the source, okay. All right, so okay, I'm remembering how this works now. All right, so if ready sample or not valid sample, drive object and not self.pause. Okay, so let me think about this here. So this is going to be and not. Okay, how about that? What if I do that? Okay, so in this case, yeah, so I'm not looking at the valid signal. I don't care about the valid signal. Okay, so in this case, see here. So bus valid set to 0. This one doesn't actually set bus valid high, but that should be done here. Okay, all right. So the way this works is this is a continuous loop. This checks the handshaking signals. In this case, I'm really only interested in the ready signal. Now, if it has something to drive and it's not being asked to pause, and the ready signal is high, then it goes ahead and drives the new value. Otherwise, it sets bus valid to 0. All right. Let's see if that does anything different this time around. And there you go. It ran correctly because there we go. Now we can see it drops. Now the FIFOs can drain out, and then they accept data in short bursts. And let's see. Yeah, they accept data in short bursts, and then it goes back to. Yeah. So this is. So the issue here is that it takes several cycles for the writes to be processed. So it gets a bunch of writes dumped on it, and then it takes a while for those writes to work their way out. Once it moves on to actually doing, DMA transfers, that's, much higher performance because it doesn't take several cycles to process, each one of those writes. The completions, for the most part, will be handled immediately. Yeah, so at this point, we can see the ST ready falls a few times here, but here it doesn't have to fall at all. Over here, it does have to fall a couple of times as it's, I guess, doing some more writes. Okay. Well, there you go. So this actually ran correctly. That was a test bench problem. It's always something that you got to be able to figure out. Is that if a test doesn't work, it's a question of, is this an HDL problem or is this a test bench problem? And it can absolutely be either one. Okay, so yeah, that actually reinforces that I think what I'm doing here is not quite correct. So in this case, I don't care about the ready sample, I only care about the valid sample. So the ready will be set that way. And yeah, then I don't care about the ready. All right, there we go. So that now fixes the handshaking. Maybe not completely, because I think for one or both of these, I need to be able to implement, or not implement, but emulate some delay. So I think what it was saying for the H tile in the receive direction, there's something like, what, 17 or 18 cycles delay between the user logic deasserting ready and the core actually stopping the flow of data. So I got to think about how to implement that properly, probably in terms of having a delayed ready sample here. But yeah, that would be the idea in terms of getting that squared away. All right, so that's probably the most important thing to fix in terms of flow control. Let's see. So I guess what I could probably do is make an attempt at getting this design running on the board. Oh, I think Quartus is actually just about done here. It's generating the programming file. Once that's done, then I can go ahead and reload the FPGA, and we'll see what that looks like on signal tap. Okay, says the assembler was successful, and now it loads the timing analyzer, so I gotta wait for that. Great. I know a lot of people complain about Vivado being slow, but I don't know, I think Quartus is a little bit slower. Alright, can I program this thing? Start, okay. Okay, so that finished. Now what I need to do is pull these windows back over here, and I'm going to go ahead and reset the FPGA. So I don't need to reboot the computer this time, because I don't need to re-enumerate the PCIe bus. But what I do need to do is run my hot reset script. That is the correct device. Yes, okay. Okay. And yep, it redetected the device again, and let's see. I should be able to go ahead and insmod it. Yep, that looks good. And rmmod it. Alright, very nice. So let's get rid of this guy. Timing analyzer is not helpful at the moment. I need to get signal tap operating. Alright. Program the device to continue. I did. There we go. Acquisition in progress. Okay. That didn't do what I thought it was going to do. What is going on here? Oh, I guess I don't have any trigger conditions configured. Yeah, alright. So what I'm going to do is set this up so every time the board sends a packet, then it will capture that. Alright, so I'm going to go ahead and hit run. Acquisition in progress. Okay, cool. So I'm going to go ahead, insmod the driver, rmmod the driver, and stop that. Okay. Something definitely happened that time. Alright, so let's take a look at what we have. Take a look at one of these triggers. Is that a trigger? Okay, so I guess these lines with a 0, that is the trigger. Okay, so this is TXST valid. There should just be one signal there, right? So there's TXST valid. There should be like RXST valid here. Okay. So this is in terms of yeah, this is one of the test reads. So it does here's the read request coming in. Here is the write response, or the completion going back out. So read request, read data. Okay, And you can see here the 11223344 that the driver writes and then reads. Okay, so what I'm interested in now is what the deal is with all of these credit-related signals here. So this is going to be, so the CPLH credits, 7F, that goes down to 7E. And then it comes back up to 7F. Interesting. Okay, so it looks like this is actually not the limit, but this is just the running sum. Okay, because if this was a limit value, I would not expect it to be behaving this way. So that's actually perfect. I was thinking I was going to have to do a whole lot of work to try and reconstruct this. So I think that actually means the documentation for this is inaccurate. Let me actually take a look really quick at the PCI Express specification here where it talks about the flow control. So we can make sure the terminology is correct. Okay, where is this here? I need to go up to the transaction layer. Ordering and receive buffer flow control. Alright, so the flow control rules. Where does it talk about this here? Okay. Flow control information tracked by the transmitter. Okay, so this is... So right now we are in the role of the transmitter here, right? We are on the FPGA, we are sending packets. Alright, so there's two pieces of information that are tracked, right? There's credit consumed, and there's credit limit. Alright, so the credits consumed is the total number of FC units consumed by TLP transmissions made modulo 2 to the field size. Which is, I think, 8 bits for headers and 12 bits for data credits. So this one, it's a monotonically incrementing field. You just add to it whenever you send a packet. And then the credit limit, this is the previous credit limit received from the receiver. Or from the link partner, if you will. Right. So it's undefined when you start, and then this one is basically just updated. Right? So periodically, the device at the other end of the link will send a new value for the credit limit. And the difference between these two determines how many credits you have available to send. Right? So this one, the receiver might say you have 16 credits. And we've consumed 0 credits. As you start sending credits, this will start going up. This will go 1, 2, 3, 4, 5. You take the difference between these two, this will be 16, 16 minus 5, 11. Okay, we can send 11 more things. Once these are equal, you can't send any more packets until the link partner issues a new credit limit update. Right, so generally, limit corresponds to this monotonically incrementing value. The problem is you can't look at only the limit and see how much you can send, right? You have to look at the limit, and you also have to look at the consumed, and based on those two you can determine, you know, how much you can send. All right. This is the specific terminology used by the PCIe specification. Now, if we take a look at what the Xilinx FPGA says here in terms of flow control, they have several different selections. You can look at transmit credits available, you can look at transmit credit limit, and you can look at transmit limit consumed, right? So if we look at this, right, credits consumed, credit limit, these are directly corresponding to these two values from the PCIe specification. But this transmit credits available, this is something that the core will compute internally as the difference between these two. So when I see credit limit, I'm thinking of this, not of the difference between these two. And if we look at the documentation here for the Stratix 10 IP core, let's see, if we look at the posted header credits, that's the net value. So I guess this is not, okay, they don't use the word limit. I thought one of these said limit. Data credit net value for FC completion. Okay, so I guess these don't actually use the word limit. I thought they did. They use net value. Okay, well, now we've confirmed what that is in the logic analyzer trace. So this is actually the way this is set up. We should be able to just directly connect this to the hard IP core. Right. So we've got, let's see, what have we got? We got posted header credits, posted data credits, non-posted header credits, and completion credits. All right. So the question now is, do we have any of the DMA operations here that are going to affect the non-posted header credits? Just to see if that's doing what it's supposed to do. Yeah, that looks like what happened here, right? We sent a packet with 7F, it goes to 7E, and then it goes back to 7F. Okay. Now, on these machines, the max read request size and the max payload size are both 512 bytes. So I think it would have sent one packet and then received one packet. Right, so we send one and then, yeah, so actually that's interesting. There's quite a delay between when this is sent and when this is updated. How big of a delay is that anyway? That seems to be like almost 20 clock cycles. Woof. Interesting. I don't think that'll be a major issue, but I may just need to make sure that we keep a close eye on the number of credits that are available and perhaps open up on that limit a little bit. I think right now I had it set to like 4. Maybe I'll need to make that a parameter. Okay. Anyway, that is progress. Let me take a look now at getting these connected in here. How did I wire it up for the ultra-scale devices? Or does it pass through? Yes, it does. Okay, so these are just directly passed through. Okay, cool. So let me go ahead and take a look at the Tcl interface then. And we're basically going to do something similar. All the information that we have, we can pass through. All the information that we don't have, I mean, there's not much we can do about that, right? Okay, so yeah. What do we got here then? We got all of this. We'll go ahead and bring that down, and we'll go ahead and update this and remove the output connections that we don't have. All right, so PX-PH credits. TX-PH credits, okay. TX-PD credits. TX-PD credits. And PH credits. Okay, I don't have NPD. And then we also have CPLH. Okay. That looks good. So if that is the case, oh, and then the other thing I need to do actually is fix what I'm reporting in the model. Let's see. That should be in here, and I need to change these to use the available instead of the limit. Okay. So with that, I think that means that we should be able to enable the credit-based flow control for the Xilinx device, or for the DMA engine. All right, let me go ahead and get rid of these credit connections that I don't have. I don't have data for either of those. I just have those. Okay, that looks good. All right, so that's the Tcl interface, and then I need to go ahead and update. Let's see, this is going to be the example design. Here we go. So this one has, yeah, so I am not using, well, I don't have this, yes, and I don't have that either. All right, cool. Okay, so the right DMA engine uses these two because this writes are posted, so posted header, posted data credits, posted data credits, and then this is for reads, right, where we have the non-posted header credits to determine how many read requests can be sent. All right, so I think what we can do then is enable the flow control. Perhaps. Well, that'll be a problem for a different day, but this is looking pretty good here. This is much more encouraging than I was originally thinking. I think maybe the reason I was confused is because I think the Tcl uses a different method for this. I think these are actually using the limit values. Yeah, so this one says TX credits limit. So in this case, you have to do a little bit more work to figure out exactly what the deal is. I was looking at this here. Well, I need to look over this in a little bit more detail, but I think more work needs to be done to interpret these values for the P-tile, and I think the H-tile is actually using, since this is using the net values or the available credits, then this ends up being a little bit easier to work with. Okay. So I guess the next thing to do then is to try to get this working on the with the DMA benchmarking design, and to see what the performance looks like. But yeah, so this is the main stuff that I wanted to accomplish today, is getting the core operational and to get a read on exactly what these credit signals are doing. In this case, they're not showing the limit value, they're showing the available value, which makes things a lot easier to deal with. So that's super good news in terms of putting all the integration together. So yeah, I guess the next step is I got to do a bunch of cleanup, which I think is going to be pretty boring, and then at some point I'll probably try to get this thing running with with Corundum on the Stratix 10 MX device. And I guess one other thing that I'm going to need to do as well is get this working with the Gen 3x16 interface. I guess I can talk about that just very briefly here. In the 512-bit mode, the thing that makes that more complicated is because you can actually have two TLPs in the same clock cycle, basically. The data, or the entire bus, is basically treated as having two buses running in parallel, sort of. So you can actually have a start in lane in segment 0, and then also an end in segment 0, and then a start in segment 1, and so on and so forth. So in the transmit direction, it's not too bad, but in the receive direction, I have to figure out how that's going to work in terms of getting all this stuff into the FIFOs and pulled apart and whatnot. So this is going to be a slightly more complicated problem for a different day. Unfortunately, I have to cross this bridge in order for things to operate on the Stratix 10 devices with the full 512-bit wide interface. But I suppose the good news is that once I kind of figure out how that's going to work, I should be able to apply the same thing to the Xilinx devices, because they also support straddling, but they don't require straddling for a 512-bit interface. So that should provide a few additional gigabits per second in terms of trying to run the link at the full utilization. So. And the great thing is, I don't necessarily have to touch the DMA engine to do this. This is just in terms of this interfacing logic that's putting all the pieces together. In the receive side, I haven't quite figured out exactly how it's going to work, but in the transmit side, there's definitely a bunch of tricks that can be played. One really stupid one is that you can insert, a write request. Sorry, you can insert a read request like right in the high order lanes after a write request, and fill out the bus that way, in addition to shifting and packing stuff as well. So I'm gonna have to do some ruminating over exactly what that's going to look like, and I think, let me take a look. I think the IP core models that I have for the ultra-scale devices don't even support that. So if I look at interface here, yeah, I don't think this even supports that. This is just going over byte lanes, and I think, yeah, so SOP, I only ever set this to 0, 1, so I need to rewrite this in order for that to work. So the thing is, the models for H-Tile, or the interface for H-Tile and for P-Tile, actually support this segmented interface. And that's why this is written in a very different format here. So I loop over the segments, and then I have all of the logic inside of that. So this one will grab a new frame, and then this will, you know, mark whether it's the first or not. It'll set the valid and SOP and whatnot, and get everything all sorted out here. So this one does support segmentation. I'm going to have to take this and, you know, modify it so it supports the PCIe kind of bastardized AXI stream implementation. They're basically doing the exact same thing, except instead of having separate start of packet and end of packet signals, they just kind of pack this into T users. So it's a little bit funky. Anyway, there's not much else that I want to accomplish today. The main thing is that, well, we got the test bench running for the DMA benchmarking design, and to do that, we had to make sure that all the flow control stuff was working correctly in the receive direction, and that looks good now. And then the DMA engine is also running on the hardware, so that is excellent progress. That is a huge step towards getting Corundum operational on this board. And then I guess in the future, I'm going to have to take a look at running this on some other devices. At some point, I'm planning on getting it to run on the Stratix 10 DX and potentially also the Aria 10, but these are all longer term things. Anyway, that's about all I have for today that I wanted to show. So if anybody has any questions, you know, feel free to pop them in the chat. But I'm probably going to close this down pretty soon here. And again, I guess I didn't mention this at the start, is that these kind of longer form, more open-ended streams, I think in the future I'm going to make available only to you know, Patreon supporters. So if you like what I'm doing, if you like, you know, these streams, you want to tune in occasionally, you know, your support would be appreciated. Also, if you like all of the open source, you know, Verilog that I've been putting together, if you find that educational or useful in some extent, you know, I would appreciate the support. And the link is in the description if you want to take a look. All right. Well, if there aren't any questions at this point, then I think I'm going to go ahead and close this down for today. Thank you to everybody for tuning in. Oh, somebody's asking, which operating system is this? On my computer here, I'm running Arch Linux and XFCE for the Windows system. And let's see, I guess, how do I have the... I'm using a combination of the Blackbird and Graybird themes because I like just the contrast. Let's see, where is that going to be? Is that under Window Manager? Yeah, so I have the style set to Blackbird here, and then I think it's under Appearance. I have the Appearance set to Graybird, and I think it looks nice. If it's all Graybird, it's a little too light. If it's all Blackbird, it's a little too dark. But I think this is a nice combination. And the nice thing about running everything on Linux is that all of the tools work nicely. So right now, both of my development machines are running Arch Linux as well. Most of the machines that we have in the lab are running some flavor of Ubuntu. So I think most of them are running 1804. Potentially we'll be upgrading some of those to 2004. I can also dual boot my dev machines here as 1804, so I can test stuff in a couple of different ways. It's occasionally a little bit of a problem running stuff under Arch because Arch uses really new kernels. So as things change there, I keep having to add more if-defs and things to the drivers, which can be slightly annoying. All right. Well, that answers everybody's questions. I think I'll go ahead and close this stream down. Thank you, everybody, for tuning in. And hopefully I'll be able to do some more of these soon, and I'll have some good stuff for you guys. All right. Signing off.